All right, good morning, everybody. This is the last bit of notes that you'll ever get from me, so that's probably an extremely positive thing. If you are watching this, you may been curious as to quiz, test, worksheet. None. There's nothing. This is just the last bit of notes. This information will be on the final exam, so that's how you'll be assessed on this. But there's no worksheets, no labs, no um, quizzes, tests, nothing like that. Just for the final exam. Also, if you are watching this, please don't forget your project is due in about a week. That was posted several weeks ago, so make sure you do that. It's 5% of your grade. It's kind of huge. The good thing about this last unit is that it's really simple. Um, really simple. So actually, let me do something here. I think I screwed something up. Present. Um, okay. So hopefully you can see that. Um, hopefully you can see it. I've kind of taken the liberty already and kind of filled in a lot of these blanks already, just to kind of help you out a little bit. But we're talking about something fairly simple. We're talking about thermal, for the most part, thermal, which is stuff that you've done before, long time, and it's just easy. It's fairly simple, and the math is simple and all that. So the concepts are very elementary. So you'll be fine. Anyway, so let's kind of go back a little bit. Um, this should be a blast from the past. The whole thermodynamics concept, the branch of physics that deals with heat and its conversion to other forms. It's not just heat, but being transferred from here to here, from the sun to you, from a burner on the stove to a pot. Um, yeah. So all that, and then and so you may remember that talk that we have the laws of thermodynamics and all that. We'll come back to that. Um, yeah, we'll define heat and all that stuff. So you got these three terms here that you are, again, I'm pretty sure you're familiar with already. Kelvin, Celsius, and Fahrenheit. You could fill in those blanks there. Again, this is a video, so you can just kind of pause it when you need to. But the T sub K is for Kelvin, which you remember from chemistry. That's the one we typically use. The other one in science we typically use is Celsius. T sub C, temperature of Celsius. And then the one that we use here in America for the most part is Fahrenheit. As always, like everything else, we use a different system than most people in the world, but whatever. You may also be familiar with this term, absolute zero. Absolute zero is zero. That's a zero, not an O. That's a zero. 0 Kelvin, or if you want to measure it, oh, I did that wrong. Pardon me, I need to change that. Or negative 273 degrees Celsius. Sorry, that should be degrees Celsius. Okay, so ridiculous. Now, according to legend and the world, we haven't actually ever achieved absolute zero. It's more of a theoretical number. But a couple years ago, a couple of science guys came really, really stinking close. The question is like, well, what would happen if we reached absolute zero on a grand scale? Nothing would happen. In fact, well, that's not true. Nothing would ever happen anymore. In fact, it would be the end of the world because all molecular movement at this point, all molecular movement stops. So that would include oxygen, carbon dioxide, water, all the stuff that you need to live. So we're not. I'm not sure we want to do this, but again, typical. Just because we can, should we? So over here, so we got some formulas here. Again, as always, you don't have to have anything memorized, but these are formulas that we'll be using. And you look closely. You have two Celsius ones. The temperature Celsius is 5/9 times, and then you get parentheses. That's key. The Fahrenheit minus 32. I want to jump down to the bottom one here. This one here, please note, look, TF, this is Fahrenheit, equals 9/5 TC plus 32. So these look really, let's see, good night. I know you've missed my drawings. These look really familiar or similar, but please notice the difference. One is TC, one is TF. This is 5/9 parentheses TF minus 32. So you would do what's in the parentheses first, then multiply it times 5/9. Here, you just go straight in the order. It'd be 9/5 times TC plus 32. So again, remember your PEMDAS here. Do the parentheses, then multiply times 5/9. And then over here, just go straight through. 9 divided by 5 times TC plus 32. And we'll do a couple of those problems later. And then you get these others. These are just simple conversions. If you want Celsius and you're given Kelvin, just subtract 273. If you're given Kelvin, blah, 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 just add 273. So that's fairly straightforward. But these are the two that people tend to get a little bit confused. Of course, the question becomes, why do we use Kelvin? Why do we have to, why can't we just use whatever, and that's fine. Well, with Kelvin, as I said earlier, you can actually attain absolute zero. You can't attain absolute zero with Celsius or Fahrenheit. It just keeps going. Kelvin basically stops eventually. It's measured in equal divisions. This is just a diagram, so it's not actually drawn accurately, but if you were to actually look at a regular thermometer, you would see that both Celsius and Fahrenheit, the little hash marks, little tick marks, aren't equal apart. They're actually they change as it goes. I don't know if you've ever noticed that before. So Kelvin is just everything's even, almost like a ruler. And Kelvin's not written in degrees. So when you give your answer, all you do is just give me the letter K for the symbol. Okay, you just K, not like up here. Whereas degrees, you don't use that degree for Kelvin. It's just Kelvin. Okay, so let's look at this here. I got my paint thing again. I know you've missed this stuff. You've missed it not at all. Again, I've seen who accesses my notes anyway, so most of you haven't ever seen me do this. Oh well, life goes on. So if we're going to do this one, a healthy person has an oral temperature of 98.6. What would that be? Sorry, it's my phone. Oh, that's embarrassing. Okay, now it's turned off. A healthy person has an oral temperature of 98.6. What would his reading be on the Celsius scale? So we need to let's go back to my notes and clip this one. We're going to take this one here. And that's the formula we're going to use for this one. Oh, man, we don't want to do that. Let's move it over here so we can get out of the way. Right? So a healthy person has an oral temperature of 98.6. What would his reading be on the Celsius scale? All right, so let's see. Hold on. There you go. Can't find my stuff here. Okay. All right. So oral temperature, that's Fahrenheit. So TF equals 98.6. By the way, this isn't accurate. Nobody's body temperature is 98.6. But let's move on, and we're going to find it in TC. So TC equals, and you know me, I like using parentheses whenever I can. And I know you're saying, no, you just said you don't use parentheses. That's not what I said. I just said make sure you do follow order operations. I'm going to put 5/9 in there, and TF is what we were given. But I'm still going to do what's in the parentheses first. We have to do this part first. So 98.6 minus 32. 98.6 minus 32. Hold on, I got my calculator. That would be, so I still have the 5/9. And then 98.6 minus 32 would equal, I got, see, 66.6. I think that's right. Is that right? Yeah. Hold on. I think my calculator screwed that up. I'll be right back. Oh, that's right. That was right. And sorry about that. I'm back. And then we would then multiply those two together. So now that's a 9, by the way. So now we can go ahead and multiply that together. So that would be times. And again, I would just put in the calculator just as it says. I think that makes it easier. I'd just do parentheses 5 divided by 9, and the answer ends up being 37 degrees, and it's Celsius, so you use the degree mark, and it's Celsius, okay? So there's your final answer for that one. Simple enough? Okay. Let's do the next one. A time and temperature sign on a bank indicates outdoor temperature 20. What's the corresponding Fahrenheit? Okay. So let's get that one up here on my paint. Let's see. Let's erase all of it. Can we erase all of it? Magic select. Stand by. Oh, stop. Let's see. Get rid of all of this. Okay. I'm sure there's an easier way to do that. I haven't figured it out how. All right. So here we go. Got another one here. A time and temperature sign on a bank indicates the outdoor temperature is -20. What's the corresponding Fahrenheit temperature? All right, let's go to that. Let's get my formula here. Which one are we going to use? We're going to use the, let's see, time and temperature indicates we need Fahrenheit. It's only got one Fahrenheit formula. It's right there. All right, like the paint here, plug that in up there. All right, so, whoops. All right, that looks good there. So let's see what we can do with this. All right, got my pencil. Time and temperature sign. So we're trying to find TF. TF equals, and this we're just going to go right in order. TF times TC, which is -20. Don't mess that up. Plus 32. So again, just type it in exactly as it says. 9 divided by 5 times -20, and that equals -36 plus 32, and that's going to end up being, yes, I tried to check my work because you know me by now, -4 degrees Fahrenheit. Okay. Pretty straightforward. Again, it's just the math, just the order of operation stuff that you need to be careful of. Okay. All right. Some more stuff down here. Some more stuff down. Sorry about that. Some more stuff down here. Just some terms. How are kinetic energy and temperature related? It's like, well, hold on. Where do we get kinetic energy from? Well, stand by. As most of you know, kinetic energy, as all of you should know, kinetic energy is the energy of movement. So if you do something like this, and of course, most of you know, obviously it'll get hot. So we're actually going to relate it. In fact, you can just kind of skip down to number 10 here. The unit we're using is a joule. You may remember that from energy and work. So these are all energy, work, heat, temperature. They're all related. So how are they related? Kinetic energy, of course, is the energy of movement. We've done, as opposed to potential energy, or that's pretty much it. Temperature is proportional or directly related to the average kinetic energy. So as the kinetic energy goes up, so does the temperature. Again, kinetic energy goes up, so goes the temperature. As the sun comes up and starts radiating down, it's making molecules move, and temperature goes up. It's very straightforward. And then the other way, and then the other side, as kinetic energy slows down and movement stops, it cools down. And if you have something that's high energy, that equals high temperature and more particle movement. You go and turn your stove on, you put the pot of water on there, high energy through the pot into the water, high energy, more water, more molecule movement, more particle movement, higher temperature. So you literally have those molecules that are bumping into each other. That's what's going on there. That's pretty much it. Okay. All right. So let's get down here. We have a term here that, just kind of be familiar with: internal energy. Why do you need to know internal energy? Well, there's this, we have a formula coming up in a little while that actually uses this term internal energy, and we'll come back to that in a minute. Well, we'll come back to it later. But the difference between internal energy and heat, so there is a difference between, so there is a relationship between energy and heat, but the term internal energy is not the same. They're not the same thing. Energy and heat are not the same. They're not the same, but they're related. So what's the difference? Well, internal energy is the sum of all molecular energy, potential energy, kinetic, all of it put together. So, you push the rock up the hill, so all the kinetic energy you put to get into it and all the potential energy that it has sitting on top of the hill, that's the internal energy, essentially, theoretically, okay? Heat is the actual movement, okay? It says transit, okay? That's movement. So heat is actual movement. And I don't know if you already knew this, but heat will go from hot to cold. Heat always travels from hot to cold. In fact, when you touch something cold, like my cold coffee mug, when you touch that, um, it feels cold because this cup is actually absorbing the heat from my hand. And I feel that the heat is moving from hot to cold. Over here is my fridge. I have an ice maker, as most of you do. I don't know if you knew this, but your ice maker should be hooked up to the hot water line. Okay, it actually freezes faster that way because the faster that the heat can go from one thing to another, the faster something will freeze. Anyway, but it always moves from hot to cold. And then the unit, as I said a minute ago, is the joule, which hopefully, as I said a minute ago, also that's also your energy, and that's also heat, and that's also work. Those things are all related to each other. And you may remember with potential energy, the law of conservation of energy, and how the work energy theorem. You know, 1/2 mv squared equals the energy. You may remember that. If not, that's okay. You can go back to your notes and look at that. Heat transfer. The symbol for heat is Q, as if of course, you don't have to know this. This isn't a formula. It's just kind of a principle. Basically says right here, heat lost by one object is heat gained by the other object or its surroundings. The heat lost by one object is equal to the heat gained by another or its surroundings. Okay, it's all, again, back to the concept of energy is neither created nor destroyed. It just doesn't like disappear. It goes somewhere. When you're outside and you start sweating, sweat's going to cool you off. It's going to evaporate, going to make you feel cooler. That heat, radiates off into the surroundings. It doesn't disappear. It just comes off you like it comes off of you, and like it already, not radiation, but the sun radiates you, but the temperature just conducts right off of you. So the heat lost by one is basically heat gained by another. Again, so it's like a conservation. And the rate of transfer depends on the temperature difference. This is what I was just getting into a minute ago. Kind of got ahead of myself. But the rate depends on the temperature difference. Again, if you've got really, really hot water coming out of your the hose behind your fridge, and then it goes right into your freezer, that transfer is going to be huge. The more heat, the faster it can go. So if you're looking at this diagram here, you've got a can, the temperature is 5 degrees. The water that the can is sitting in is 35. And you see all these red arrows. The heat transfer from hot to cold really fast because there's a 30-degree change here. Take over here, you got a can that's 15 degrees and the water's 20. It's only a 5-degree difference and you only have a few arrows. Two things to remember. Number one is that heat temperature goes from hot to cold. Number two, that the greater the temperature difference, the greater the energy transfer. In fact, there it is right there. Here's what I just said right there. The greater the temperature difference, the greater the energy transfer. Again, the bigger the hill, the faster the fall, if you want to look at it like that. So here it asks, what do you think would happen here? The temperature of the can is 11, the temperature of the water is 11. Well, if you look close, you'll see arrows going in and out, and this is called thermal equilibrium. Thermal equilibrium, thermal temperature equilibrium, which it just kind of doesn't stay put, but it's pretty much what goes in, what comes out. It's basically the same. Again, at any point, please pause this video so you can fill in these blanks. I'm probably not giving you enough time to fill in as we go, so just pause it as you go. I know that's a little bit frustrating. I'm not doing it to frustrate you. So just real simple, Bob is drinking a cup of coffee that's losing 468 joules of heat. How much heat is Bob gaining? Okay, you drank 468 joules of coffee heat. How much is he gaining? He gained 468 joules. Gotta be harder than that. No, it doesn't. That's it. So it's what goes in comes out, or what goes out goes in, or gets transferred from point A to point B. All right, that's easy. So there's no formula. It's just it. It's basically a concept. All right, so 468 joules. And then down here, which would have the greatest amount of energy transfer? Ice 0, juice 20, ice 0, juice 35. This is the greater one. So the answer, of course, would be B. So we're going to finish up here with this section of notes, and I'm going to make sure that these notes even recorded. The thing I usually use for notes isn't working, so hopefully this is working. If it doesn't, I'm not going to be terribly happy about that. Let me make sure it's even recording now. Yep, looks like it is. Yeah. I got it. Thank you. All right. So again, I've already filled these in for you. Um, these terms here, conduction, convection, radiation, I am not going to be dopey here and think for 1 minute that you haven't heard these terms before. I know you've heard of conductors because we talked about it in electricity. So anyway, you've got three types of heat transfer: conduction, convection, radiation. You could look down here. Here's conduction, like you touch a hot pan. Convection is the water vapor or whatever that comes off as you boil water. And then radiation is like a fire or sun. Okay. So what is it by definition? Conduction is the actual vibrating of the molecules. They transfer thermal energy to nearby molecules. They basically bump molecules. They bump into each other. And just like with electricity, there are conductors and insulators. Conductors transfer the molecules rapidly, and insulators transfer slowly. In fact, just like electricity, electrical conductors are typically really good thermal conductors. So copper is great. That's why some of you may have copper bottom plates, pots and pans. Conducts heat really, really well. And of course, we all know it does electricity really, really well. Glass, you know, glass is a good insulator. Yes, I know you've got pots and pans um, that are glass, but they cool off pretty quick too. Okay, so and other things that are actual electrical insulators make pretty good uh, conduction insulators. Again, remember water? Well, everyone thinks water is an electrical conductor. It's not. It's the stuff in water. Pure water is a terrible conductor. It's a nice insulator, though. Not saying go dip yourself in water to stay warm, but sometimes it's warmer in the pool than it is in the actual outside. Okay. Anyway, so the point is that typically good electrical conductors make good thermal conductors, and typically good electrical insulators make good thermal insulators. Typically, not always. Convection is the heat carried by bulk movement of fluid or gases. That's the key concept there, the fluid or gases part. So again, convection. In fact, they make convection ovens. Some of you may even have a convection oven in your home. It's not about, some of you have a heating element or things like that. That's not the same thing. Okay, that's a different kind of oven or stove. But convection by the bulk movement of the fluid or gases. So you can see here, like down here, with this like a little steam cloud coming off the pot. And then finally, the radiation, transferred energy by electromagnetic. No, we're not getting back into EM, but that's, we already did cover that 1,000 times. X-rays and gamma, blah, 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 blah. Ultraviolet, infrared. In fact, we're, it's still still nice, cool weather here in May, but eventually, once July and August hits, we will be getting plenty of electromagnetic radiation in terms of ultraviolet, and radiation is transferred energy by the EM waves. The heat comes when you stand outside in the sun and you feel hot. The heat comes. Sorry about that. Little note from one of my teachers. The heat comes from absorption of those wavelengths. So why do you feel hot? You're actually absorbing radiation. You are absorbing radiation, which, by the way, if you go out to sunbathe and all that stuff, that's your prerogative. But please know that you are absorbing radiation. Everybody knows, and there's no debate about this, radiation causes tumors. So please put on sunscreen. That's right. Public service message. Use sunscreen. You got a nice long life to live. You want to live that nice long life. So down here, so this it's whatever. So I've got 1, 2, 3, and if I was in class, I'd say what is 1 representing? What's 2? What's 3? Well, 1 would of course be conduction, because this is a metal pole over the fire. You can see it's starting to glow. He's got a glove on for safety, and that's conducting. The molecules are bumping into each other, vibrating, causing the heat. Over the same fire, someone is warming their hands, and that's the convection, the gases. That's the gases. And then you literally have the electromagnetic waves off to the side. Well, what can't these be this? Yes, they can, but just for the sake of example. Okay, so I'm going to pause there, mainly because that's enough for now, and I'm going to make sure that this video even recorded anyway. So, and again, you go back and do anything you need to do. It's your video. It's your video to have in the whole. Okay. See you later.